Okay, so what this is normally called, you'll hear talk of heterodyning or super heterodyning, and what that is that it'll take a signal and shift it from one frequency range to another by this difference on the outputs, and then you can filter which uh, frequency you want to use, and then continue on with your circuit. So this mixer will generate the main frequency F1, the input frequency at two different frequencies, either plus F2 and minus F2. There's a frequency multiplier where, whoops, got carried away there. Oops, I'm on the wrong. Yep, we got the frequency multiplier, and what it does is it generates harmonics of the input signal. By harmonics, what that means is it takes the input signal and it'll multiply it by 2, the frequency by 3, the frequency by 4. So you get all these different frequencies coming out that are multiples of the input frequency. And then you can use a filter to select which one of the harmonics you want to use as you go on through there. So this is just another building block, and we'll see how all these fit together in transmitters and receivers to do the various functions that we need to do. So with the mixer we just looked at, we're able to modulate an audio signal on a constant frequency, constant magnitude sine wave, and that'll give us the modulated AM signal or single sideband signal we want to transmit. Um, then for frequency and phase modulation, the book had a couple examples here um, where you take the audio input, run it through an audio frequency amplifier, and go through a reactance modulator that feeds an oscillator. And so this would be a variable frequency oscillator where you change the voltage, you change the frequency, and then you get the frequency modulated output. So as this audio signal changes in uh, magnitude and frequency, then the output frequency of this section, the frequency changes with the input audio signal. And then this diagram here is showing how you use the reactance modulator and the oscillator that you used here, and instead of doing the output being the frequency modulated output, then we get the phase modulated output. So these building blocks can be put together in different ways to accomplish different things that we want to do in the system. And this also is an example out of the book, and this is showing one of the simplest transmitters you could have, a CW transmitter, where what you're wanting to do is to transmit a signal of a certain time duration, depending on whether it's a DID or a DAW, by controlling the on time with the key. So you either use a variable frequency oscillator or a crystal oscillator to get you that constant magnitude, constant frequency um, sine wave, and then drive an amplifier with that you can turn off and on with a key. So when the key's closed, you transmit that frequency out the antenna, and when the key opens, the amplifier shuts off, and you're not transmitting. So if you held this for a very short period of time, you can transmit a DIT, and if you hold it a longer period of time, you can transmit a dot. So by um, you're effectively modulating this oscillator by turning the amplifier off and on, where the output is representative of your dots and dashes. And then this is kind of a whole more of a whole system, one way that you could have a single sideband transmitter. So we start off here with our microphone, which is where we started at the beginning of this discussion. And the microphone signal is amplified by some uh, audio speech amplifier. And then an oscillator generates the sine wave, and then the modulator will impose the speech signal on this sine wave. So we get that AEM looking or single sideband looking sine wave, run it through a mixer or a filter, excuse me. And what that does, it would just clean up the signal a little bit, trying to reduce some noise. And then that goes into a mixer where there are different oscillators. In this case, these are crystals that you would change different crystals to get different transmission frequencies. And it's pretty common in the older legacy equipment. This is probably done more now electronically than with the crystals. So you take that oscillator, get your mixer to multiply it together. That's where this is called the heterodyning. And then filter to clean things up, linear amplifier of some sort to get the low power signal up to a high enough power that you'd like to have to transmit, and you transmit it. So this is how the signal, the audio signal, is built to get ready to transmit. Now there's some questions on the test that I just thought I'd address without a whole lot of explanation. Split mode is a mode of operation where you're transmitting and receiving on two different frequencies. And we looked at that on VHF, UHF repeaters, where it was a split mode and that we would receive on one frequency and transmit on the another frequency. And the same thing can be done on HF with a single sideband. And there are a lot of different reasons that you would do that I'm not going to get into. But just remember that split mode is transmit and receive on two different frequencies. This next one is in reference to vacuum tubes. And I just vaguely know a little bit about vacuum tubes. So I think the best thing you could do on this question, when they talk about grid dip, just remember what the answer is. Automatic level control is a measure of the amplifier output level. And what it's used for is to help avoid output distortion. If you drive an amplifier too hard, what happens is, say you've got a sine wave going in, and you get a faithful reproduction of the sine wave coming out, but at a higher power level or higher voltage level. If you drive that too high, say the gain, if you turn the gain of the amplifier up too much, then it'll flatten out at the top because the amplifier can't go any higher in its output, even though the input's trying to make it go higher. And that flattening out is a distortion, and then it'll come back, and as it comes back within the rails of the amplifier, it'll start following that input. But the flattening is a distortion that causes problems with the quality of your audio that you're transmitting. So it's not always good to have as high a gain as you can, because you can add a lot of noise that way. And just it's almost a given. Excuse me. Excessive drive power is never good. So if they're asking you a question about excessive drive power, just remember it's never good, and then you'll be able to figure out the answer. Okay, now we'll take a look at amplifier classes, and they cite 4 different classes in the manual. There are a lot of other different classes for different situations, so we'll just touch on the 4 that they covered there. The first one's a Class A, It's a linear amplifier, meaning that the output follows the input. And it's a design where the output devices, the transistors, are continuously conducting. And as a result of that, it only has about 20% efficiency, where say if you wanted 100-watt output, you could be losing as much as 400 watts just due to the design of the circuit. So that has a big impact on your energy consumption. So a Class A amplifier would amplify continuously through a whole cycle like that. A Class B amplifier is also a linear amplifier. The output devices conduct for half of the sinusoidal cycle. So there'll be two of them, two amplifiers stacked, and we'll look at a schematic on the next slide. Two transistors stacked one on top of the other. One transistor is providing the gain in one half of the cycle, and the other transistor will provide the gain on the other half of the sine wave cycle. One problem with this type of amplifier is that there's a little distortion at the crossover as one transistor is turning off and the other one's turning on. You get a little distortion. So in order to address that, there's a Class AB amplifier that you can use, where it amplifies one of the transistors, will amplify through more than just the half cycle, and then the other transistor will do more than just its half cycle. And we'll look at a schematic of that. It's a little more complex, but you get you address the problem of the distortion at the zero crossover point. And of these four classes, the Class C is the most efficient. They're citing at around 70%, and that's where output devices conduct for less than half of the cycle. Highly nonlinear in distortion of the audio input. So they're a little tough to use for the audio applications. So if we take a look at those four classes, this is showing a Class A amplifier. It can be realized with just a single transistor and a resistor, and you get the output higher magnitude than the input, which is what an amplifier does. And you can also see there's a phase reversal, where when this one's going positive, the output's going negative. So that's a Class A, best for low level signals. Receivers do low distortion because the transistor doesn't have any trouble going through the zero cross point, because it's biased. Say if it's a 10-volt power supply, you would typically want to bias the transistor with the biasing resistors to hold this at, say, plus 5 volts. So it may go then from 5 volts down to close to 0, and then back up to 10 is the operating range. So there's no problem crossing over what is the signal's zero level. And then a Class B that does one half cycle, and then another transistor doing the other half cycle. You can see there are two transistors, and I've heard this referred to as a push-pull amplifier, totem pole amplifier. But the way it works is, if you have a sine wave input, this transistor amplifies this section of the sine wave, and then this transistor amplifies this section of the sine wave. So you can see where it's a little non-linear when you get down to 0 volts, because there's the forward bias voltage of a transistor. If it's a silicon transistor, it's about 0.7 volts. Germanium's about 0.3. So there's a little discontinuity when it goes through the minus 0.7 to plus 0.7, and causes a little distortion on a Class B amplifier. So like I mentioned, the Class AB is a design to address that crossover problem. And one way that it can be taken care of is by the addition of a couple diodes here um, to compensate for that bias, forward bias voltage of the transistors, so you don't get the distortion at the zero cross that you did. And then Class C is it's just kind of like a pulse. It pulses on once you get over a certain threshold in the sine wave. And so it's just at a single fixed carrier frequency. So that would be, you could do CW with that, for example. So those are the four main classes. And it's just like everything else in engineering. The reason for the different designs is that there are trade-offs that you have to make depending on what's important to you for the circuit operation. And that's why there's even more types of amplifiers than what we're seeing here. Okay, now we're going to take a look at an FM transmitter. And this is the block diagram that was in the book, where they're showing a microphone driving a speech amplifier, the reactance modulator, to an oscillator, so that you get your variable frequency, a multiplier, a filter, an amplifier, and then the antenna. Now, this is the same type of diagram, but what I liked about it was it was showing the waveforms at the different points in the circuit. So here, this is the audio signal coming in, and then on 2, the modulator modulates the carrier frequency with the, I think I've got that wrong. I'm not sure what. Oh, this is just the audio stage. Excuse me. I got off a block there. So this is the audio signal. The first stage is an amplifier that makes the audio signal stronger, higher powered, more voltage. Then here at 2 and 3 is where we take the constant frequency, constant amplitude sine wave, and modulate it with the amplified audio signal, and the output of that is the frequency modulated signal. And then we go through yet another RF amplifier, we get the power level up. You can see we're going from here to here, so we can get generate more energy being radiated, and we go out the antenna. So that's how an FM transmitter will work. And then the FM receiver, it's kind of just this process in reverse, where here we're constructing the signal we want to transmit. On the receiving end, what we're going to do is we're going to take that signal that was transmitted and deconstruct it so we get the audio output. And it goes through the RF tuner. The antenna picks up a wide band of frequencies. We use the RF tuner. It's a filter that'll just take a narrow band that we want to listen to. Then we'll go from an RF to an IF converter with a mixer, and that's it shifts the frequency from whatever the receiving frequency is to what's called an intermediate frequency in the radio for further processing. And we filter that IF signal. On FM, the amplitude carries no information about the audio signal. The audio signal's information is contained within the frequency variation, so they will limit the magnitude coming out of this section of the amplitude of the signal. And that's one reason that FM radios in your car, for example, have much better sound or less sensitive to atmospheric conditions like lightning than an AM signal. Because if you get a lightning crash on an FM signal, this amplitude limiter will just take that out. without losing any of the audio signal information, because all of that information is contained in the frequency variation. Whereas as on an AM signal, since the information is carried in the amplitude of the carrier signal, if you add to that signal with lightning, for example, that's added to the audio signal you're trying to transmit, and becomes very noisy. Then demodulate the FM signal to get it back to a time signal that the audio signal looks at. And then they use a de-emphasis network where they de-emphasize the higher frequency components of the received signal to take out noise. And then that goes to an audio amplifier and then to the audio output. So it just kind of deconstructs that frequency modulated signal to get back to the audio output, which should be as nearly identical as the audio input as the transmitting station had. Now we're going to take a look at filter types. And what we're talking about in terms of a filter is a device or a circuit that passes certain frequencies. And there are several different types of filters. We've seen some of these already, but these are characterized as ideal filter response curves. And for example, here a low pass filter would only pass low frequencies up to whatever the limit frequency is, and then completely block the higher frequencies. And the reason this is called an ideal filter is that it absolutely cuts it off with no higher frequencies getting through. But the fact of the matter is that a low pass filter, this drop is typically around the knee, and it comes down and never really does eliminate completely 100% all the higher frequencies. So there are ways of making this drop-off rate sharper, so you do a better job of eliminating the higher frequencies that don't recall if we'll get it. Yeah, we'll probably get into that. The Q of the filters, the higher Q filters have sharper drop-offs and do a better job of eliminating the higher frequencies at the cost of a more complex circuit and usually more expensive. And then there's a high pass filter that's just kind of the mirror image of a low pass filter, where it stops all the low frequencies, but it'll pass all the frequencies above a certain frequency. And the high pass filter here also has a similar knee and taper in an actual filter. Then a band pass filter lets a narrow band, or however wide a band of frequencies you want to pass through it, and it's kind of a combination of I guess it'd be the inverse of the band stop filter. Band stop filter would pass lower frequencies and higher frequencies and stop the center ones. So if you took two of these and put them together, that's what a low pass and a high pass filter would do. And then the band pass filter would only pass frequencies in this narrow range. This is the kind of filter, and it would have to be adjustable if you were using it to tune a receiver to listen to different frequencies. So as you move the bandpass window, you'll let through a different range of frequencies than you had before, and that's how you tune a receiving antenna to just let in the frequencies you want. So filters, there's three basic ways of producing filters. One is using passive components, which would be inductors and capacitors. And if you recall, when we talked about reactance of capacitors and inductors, they both behave actually opposite, nearly opposite, in terms of reactance as a function of frequency. So that an inductor the reactance increases as the frequency increases. Whereas with a capacitor, the reactance decreases as a function of frequency as the frequency goes up. So by using those two devices in particular combinations and values, you can generate low pass filters, high pass filters, band pass, and band stop filters. So those are done with passive components, inductors, and capacitors. You can also do the filtering function with active components. And by active component, one of the best examples would be primarily for audio frequencies, would be an operational amplifier, because you can design all these different types of filters with varying steepness of cutoff with op amps or transistors. The trade-off being is that you can get better performance at a higher cost. So again, it's going to come down to the trade-off evaluation, and the engineer would go through in determining whether his particular application would require, could be satisfied with passive components, or if the requirements were such that he would have to have better performing filters, then he would could use active components to design the filters. And then the third type of filter that you'll encounter is a digital signal processor. And I think I covered that on the next slide, or maybe a later slide. Let's see. Okay, this is going back to the passive components. So the passive component filters look like this, where you have an input signal, and it'll be an AC signal. It's going to have to vary because at DC, an inductor is a short circuit and the capacitor is an open circuit. So you have to have some AC action in order to enable the capacitors and inductors to store and release the energy. So a passive low pass filter, get my mouse going here. I don't know why I keep losing my mouse. So this is a passive low pass filter. It has a resistor. Whoops. I'm going to stop the video or pause it. Wow, I was just offered an electric bill rate reduction. So I hung up on her. Okay, so we're looking at a low pass filter, and it's a resistor with a capacitor. Now, if you recall, as the frequency increases, the reactance of this capacitor will decrease. So the value of the resistance or reactance will get smaller and smaller. And so what you really have here is an AC voltage divider circuit. So when this capacitor and the frequency is at a point where the reactance of this capacitor is very high, which would be at a low frequency, you get pretty much 100% of your signal going through. But as your frequency increases, this capacitor reactance decreases, which makes this more and more of a heading towards a short circuit. So most of your voltage drop will be here as this reactance increases, and this voltage here, the voltage level will go down, down, and down, so that at a very high frequency, this will look pretty much like a short circuit. So that's how the resistor and capacitor work together in a voltage divider with reactances and resistances to do a low pass filter. And if you look here at a passive high pass filter, the capacitors in series. If you had very low frequency, this would be a very high reactance. If you were DC, it would completely block the current flow, so there would be no DC pass through here. Then as this reactance decreases, it gets, or increases, excuse me, decreases because we're going down. As this goes down, more of the voltage drop is here, so we're getting more of the higher frequencies passing through on this high pass filter. So that's how a high pass filter works. It's just a reactance and resistor voltage divider where the reactance changes as the frequency increases. So it lets more and more of the high frequency components through. And then the passive bandpass filter is just a combination of the two, where at the higher frequencies, this becomes more of a short. This becomes more of a short. Then you would have to size these capacitors so that one would, they wouldn't be about the same size. So that's a general configuration of three types of passive component filters. The other type of filter, and you can do those passive filters that we just looked at with op amps and for active filters, and you can get a lot more capability, higher performance out of the active filters than you can the passive, at the expense of more complexity and more cost. So the third type of filter we talked about was a digital signal processor. And this is something that's been around for a while. I mean, it's been around so long, I actually studied this in school over 40 years ago. What's changed has been the technology, the components, and the system architecture to do these kind of things. But basically what a digital signal processor does in terms of filtering is you take the analog signal that's coming from, say, the receiver, and you've got it into the IF stage, and you want to filter it. So you take the analog signal and you do an analog to digital conversion. Now, what that does is it takes and generates a number output that is proportional to the input voltage that it's seeing. And it does it very fast, so that the whole time this is running, let's say it's got a 1 megahertz clock, it's taking 1 million readings a second and passing them on to the digital signal processing. So it'd be like taking a picture of a digital voltmeter 1 million times a second and using that information, passing it on to the little computer. And what makes this so powerful is that once you get it into digital form, then your filters are not components, neither passive nor active components, but they are equations. And you can, if your processing's fast enough and you're clever enough in your equation design, to do some pretty neat things with the digital filters, and then coming out of the digital filter, which is just another string of numbers, numbers representing the modified input signal. Then you drive those through a digital analog converter and get it back to a variable voltage, and that's the analog signal. So all the work's done in here in the math, and there's just a lot of neat things you can do with it. So this is another way, it kind of shows a little more detail of what goes on with digital signal processing. So you have some signal coming in, and you take the analog to digital converter, and it converts it to numbers representing the input voltage. The microprocessor performs the calculations, generates output numbers, and then those output numbers are fed through a digital analog converter, and you will have a new waveform, or can have a new waveform, depending upon the transformation calculations you do at this point. So it's not that you can't do the same type of thing with active components, but it's just a lot of versatility when you can get it into the digital world. So the receiver structure, we talked about transmitters, now we're looking at receivers. And there are three that we're going to take a look at. One's the super heterodyne, used most commonly with AM and single sideband. Then the latest, I guess you'd call it a revolution in technology, has been the software-defined radios. It also can do AM and single sideband. We'll look at that. And then the FM radios. So this is kind of a busy slide, but what it is that if you look at this, this is the receiver that we looked at earlier. I believe we looked at it earlier. Anyway, you bring in the signal from the antenna, go through an amplifier of some sorts, and then you mix it with the local oscillator. Now, you'll see references to something called the IF stage, or the intermediate frequency stage of the radio. And the reason for that is that if you think about what we're expecting out of this radio on the front end, we want to be able to receive everything from, say, 160 meters to 6 meters, and be able to tune it, filter it, do all sort of manipulations to it. So if you had to design a radio to do all those functions that you need that's downstream here over this wide of a frequency range, it would need to be an extremely large complex radio, because all the values that you're using for your filters and your amplifiers and things like that are sensitive to the frequency. So depending on what frequency range you're in, you'd have to have different components. So rather than trying to do that, what happens is you receive whatever frequency on those bands you're wanting to hear, and depending on, you bring it into the radio and use this mixer, and it shifts it to an intermediate frequency, which is the same frequency regardless of what band you are bringing the signal in from. So that you've got the, from this point forward, you know what frequency you're going to be dealing with, and the design can be much simpler because it's all going to be done at this intermediate frequency value. So that's how you can take a radio from 1.8 megahertz up to 50 megahertz and do all this neat stuff on it by doing this heterodyning process. And if you look at what that does on the frequency spectrum, is this is the stations that this particular radio is hearing. It's having 4 different radio stations that the antenna is picking up. So they'll filter, there's actually more than that, but they're filtering down to this range of frequencies. And then they will, depending upon the carrier frequency, they will use this mixer to shift all of these down so that this signal is here at the intermediate frequency. Well, no, this is the RF filter. It filters out all this noise here, and this is what you're left. I've got ahead of myself there. So this is what you're hearing on the antenna. Use an RF filter just to select these frequencies and pass them through. And then here is where you do the super heterodyning, the mixing, and it takes all these frequencies and shifts them down so that they're centered on the intermediate frequency. So these are exactly the same frequencies, but shifted in frequency down here. So we can use the IF filter, because this is always the frequency we're going to work with in the radio once we get to this stage, and filter out that one signal that we want to operate on. So it takes all the signals that receives on the antenna, filters out the band of interest, and then shifts the result of that down to the intermediate frequency, and then you go from there. So each radio has a different intermediate frequency, but they all typically kind of go in that direction of this type of process. So that's what the super heterodyne for AM and single sideband does for you. There's a lot more verbiage here if you want to read it. Now, software-defined radio is another approach where it has much smart antenna, I guess they call it. And essentially what you're doing is bringing the signal in, you process the incoming RF signal to be ready to be converted to analog to digital. And then once you get the digital signal in, then the computer inside actually does all the work in processing the signal rather than active components like you have in a single sideband. So you've got one of the things you'll hear reference to on software-defined radio, particularly in the advertisements, they talk about direct sampling A to D converter, which means that they're sampling the frequency signal at that frequency to do the analog to digital conversion rather than doing some sort of pre-heterodyning to get the frequency of the signal coming in at a lower frequency so they could use a less capable A to D converter. I think the big thing to keep in mind on the difference between super heterodyne and the software-defined radio, and this is entirely my opinion. I think the distinction between the two, I can't see an instance where it would be a determining factor on the first radio you buy. I think the product offerings at that entry-level HF radio, they all, from the main suppliers, they all would do an excellent job of what you're wanting to do as an entry-level ham on HF, and it's going to be some other feature that would sway your decision between one choice or the other. But like I said, that's just my opinion. I think the actual performance differences between the super heterodyne design and the SDR design, I don't think the initial ham getting their general license is going to, see any real difference. Like right now, there's the two main radios at the next level of radio, at least what I would consider the next radio, is like I've got a Kenwood TS890. It's a super heterodyne design. I've seen, and I know people that have the ICOM 7610, I think it is, and that's an SDR radio. And based on everything I've seen, they both do a really good job. And I'm not too sure. I think it just comes down to personal preference on that. But I've heard some guys swear up and down, oh, you make a mistake if you buy a super heterodyne radio, you ought to be getting an SDR. And I don't believe any of that. I think, you got a current design, a quality supplier. They're going to do what they say it does, and it's going to be some other feature that will determine whether you select their radio or someone else's. I don't think this is a defining factor. But I'll quit talking about my opinion because there is a lot of hype on all this stuff. That's what most of it is, in my opinion, just hype. FM receiver. We looked at this a little earlier. This is just another block diagram of it. Just another way to look at it. And then the broad field of digital signal processing. I forget if this may be out of the book, but there are four most common functions for digital signal processing. Signal filtering, we talked about the low pass, band pass, high pass filters. You can do that with digital signal processing. Noise reduction. There's a whole lot of study and literature on noise reduction using digital processes. The notch filtering, that's handy. A lot of the radios will have, HF radios will have a notch filter, so that if you have one particular frequency where there's noise on it, it could be another station or just any kind of source of noise, you can put a notch right there and it'll filter out that frequency band, so you don't have to listen to it. And then audio frequency equalization. And what that is, it's just like an equalizer on your stereo, but it's some radios have them where you can adjust the gain of each of the frequency bands in the audio signal to boost the bass or boost the treble or shape it any way you want. I think on my new radio it has, I don't know, 6 or 8 preset equalization patterns, and then you can make your own custom ones. That's all done with digital signal processing. So it's a pretty neat tool. This is a look at noise and interference in your shack. So this is kind of a shift from what we were talking about now to the actual mechanics of putting your HF shack together. And grounding is a topic that gets a lot of attention. I think there's everybody has an opinion, but I think there's some fundamentals you need to keep in mind for grounding to try to minimize noise and interference in your shack. This is a good example of a properly grounded system where there's a main ground bus. In this case, it's a 1/2-inch copper pipe going through the shack, and then each component is, the ground of each component is connected to that common bus going through the shack, and then that is ultimately connected to a ground rod in the earth. And the key here is not to daisy chain these things, but to directly connect each piece of equipment to the main bus going through. And it doesn't have to be a copper tube. They've got braided stuff. You can use heavy gauge wire. I think sometimes some people get a little carried away with it. And actually in practice, to be honest, I've got my base station grounded similar to this, and I really don't notice any difference between my radios operating here and when I operate them portable in the field with no ground. So I'm not sure, but I know that this looks like a good way to do it. And the book hits some key points on noise and interference. These are 5 that I pulled out of there. The book covered it pretty well, and it had a little section in there on overmodulation. You'll hear people refer to that occasionally. So you could follow up with that in the book. And that's all I know. So I'll finish this up and get it onto YouTube probably this afternoon or evening. And I'll send you guys an email with a link to it. And if you have any questions, don't hesitate to get a hold of me or send me an email or whatever. We'll see you for the next one. I guess I'll say 73, and it's K3 SKS, and I'm done. Thank you.